Okay, topic 2.3, periodic trends. What you're looking at is just kind of a nice pictorial of the trends we will be looking at: atomic radius, electronegativity, and ionization energy. We'll be looking at melting point in our next unit on ionic bonds. Okay, now I'm going to show you this. This is actually the last slide, so just give you a little preview of where we're going. This box here represents the periodic table, and what we'll find as we move across the periodic table, as we go across from left to right, or as we go up or down, we'll find that there is a trend in the physical properties of the elements, specifically the radius of the atoms, and then what's called the ionization energy and the electronegativity. Specifically, as we go up or across, which is this diagonal arrow here, the atomic radius decreases, ionization energy increases, and electronegativity increases. All of that will make more sense to you, but I thought this would be a nice thing to take a look at to kind of see where we're going. Ultimately, you're going to be asked to compare atomic radius, ionization energies, and electronegativities of various elements based upon their placement on the periodic table. So it's really quite simple. You just need to find the elements that you're being asked about and say, okay, well, which one is the larger one, which ones have the greater ionization energy or electronegativity. So it's fairly straightforward. All right. So we're going to look at each one of these trends one at a time. Now, let me clarify the term trend. Trend is a general, tendency for something to happen. It's not written in stone. There are exceptions, but you are not responsible for the exceptions. Actually, you would have to wait until you get to IB Chem 2, where those exceptions are discussed. All right, first, atomic radius. Distance from the nucleus to the outermost electron. So you can just draw a simplistic diagram here, just from the center, the nucleus, to the outermost electron, whatever electron that might be. That's the atomic radius. Okay, now this is the periodic table where we have the relative radius of the atoms as we move around. Now, as you notice, as we go down, the atoms get bigger and bigger and bigger. And as we go across, they get smaller and smaller and smaller. So why is that? Well, the trend decreases as you go across because as you move across a period, or decreases as you move across a period due to an increase in the nuclear charge, more protons. So let's just take a look at period 2 here. So as we go across, remember we're adding electrons to the second energy level. So these two electrons here, lithium and beryllium, are the 2s electrons. And these are the 2p electrons. They all belong to the same energy level. Now, what's going on as we go across, yes, we're adding more electrons, but we're also increasing the number of protons in the atoms. Lithium has 3 protons, beryllium has 4, boron has 5, 6, etc. So as we go across, it's as if we're turning up the positive charge of the nucleus, and we're pulling in the electrons more and more tightly. So as we go across a period, the atoms actually get smaller and smaller, even though we're adding more electrons. Again, it's because we're adding more and more electrons to the same energy level. All the while we're doing that, we're turning up the positive charge of the nucleus. So the atoms get smaller as you go across. Now, conversely, as we go down a family, the atoms get bigger and bigger and bigger. And why is that? Well, of course, as we're going down, we're adding electrons to a higher and higher and higher energy levels, which are further and further from the nucleus. So increases as you go down a family, higher energy levels are occupied. Now, ultimately, like I said earlier, all you need to know is the general trend. So if I was to ask you which atom is bigger or smaller, lithium or beryllium, well, beryllium, because the atomic radius decreases as we go across. If I was to ask you to compare lithium and sodium, sodium would be bigger because the atomic radius increases as you go down. Okay, now, kind of a simple way of comparing is to look at the two extremes. Francium down in the far left corner here is the largest elements. Remember, atoms get larger as you go down, smaller as you go across. So francium would be the largest. Conversely, helium would be the smallest. Atoms get smaller as you go across and larger as you go down. So as we go from francium to helium, the atomic radius gets smaller and smaller and smaller. Okay, so let's see how we can determine relative size. Circle the element with the largest atomic radius. So now you're not going to be just given any random 3 elements. They're going to be something related. They're going to be related in some manner, either in the same period or the same family or just close to one another. So magnesium, calcium, and strontium are all right here. So which element has the largest atomic radius? And you can pause the video and try to do it yourself. But remember, we just talked about that the atoms get larger as we go down. So strontium would be the largest of the 3. So see, it's pretty simple, pretty straightforward. Another way of looking at it is, well, it's largest because it's closer to francium. Let's do another one. Circle the element with the smallest atomic radius. So that's over on the other side of the periodic table. So arsenic, selenium, and tellurium, they're right here. So what we want to do is to look at which one is the largest. Which one's the smallest? So remember, as we go across a period, the atoms get smaller and smaller. So comparing arsenic and selenium, selenium would be the smallest. And then also atoms get larger as we go down. So selenium would be both smaller than arsenic and smaller than tellurium. But we could also say, well, gee, it's also the one closer to helium. And helium, again, is the smallest. Okay, next trend, ionization energy. It's the energy required to remove the outermost electron from a gaseous atom. Now, we have to have that qualifier, gaseous atom, because as you'll find in our next few units, atoms are typically bonded together. And so when we're talking about removing electrons, we have to be referring to an atom that's not in a compound. It's all by itself. And that's what's meant by a gaseous atom. So don't worry about that too much. This is a representation of that. So any element, gaseous, and an electron is being removed from it. Of course, that would make it a positive ion. Okay, now smaller atoms, have the electrons closer to the nucleus. And so those are going to be more tightly held. Just think of it like a magnet and a piece of metal. The closer the metal is to the magnet, the stronger the attraction. Just the same thing. The closer the electron is to the positive nucleus, the stronger the attraction. So it's going to be harder to remove an electron when it's closer to the nucleus. Conversely, for larger atoms, the electron is further from the nucleus. So it's going to be easier to remove. So the trend for ionization energy is that it's inversely proportional to the atomic radii, meaning the larger the atom, the smaller the ionization energy, because the electrons are going to be more easily removed. Okay, to kind of spell it out here completely, the trend in ionization energy increases as you move across a period. And when we say that, we mean left to right, like reading. Atoms get smaller, electrons are closer to the nucleus, and harder to remove. And decreases as you move down a family because the atoms get larger. Electrons are further from the nucleus, and therefore easier to remove. Now, I encourage you to just use this first line here to determine ionization energy or relative ionization energy. It's just simply inversely proportional to the atomic radii. So we just talked about how we can determine if an atom is larger or smaller, and so it would be just the opposite for ionization energy. The larger atom would have the smaller ionization energy, and the smaller atom would have the larger ionization energy. Okay, now you don't need to copy this down. I just thought you might find it interesting. This is a chart of the ionization energies for individual periods. So this would be the first period, hydrogen to helium. This would be the second period, lithium all the way to neon. Third period, sodium all the way to argon. And fourth period, Okay, let's take a look at the second period. So remember, I talked about there being exceptions to these trends. And this is a good example of that. So yes, the trend is as we go across a period from lithium all the way to neon, the ionization energy increases. But you can see there's a couple of exceptions there. Boron is an exception. Oxygen is an exception. Now, you're not responsible for those exceptions. But it's really quite interesting, those exceptions, why that is. But it's something that you'll have to wait till you get to IBGM 2 to learn about, unless you want to investigate that on your own. Okay, let's do some practice. Circle the element with the largest ionization energy. You have chlorine, selenium, and bromine. And they're right here. Now, the hint will be just find the element that is the smallest. Remember, the smaller the atom, the larger the ionization energy. Now remember that the atoms get smaller as you go across a period. So if I was just to compare selenium and bromine, bromine is going to be the smaller. So of the two, bromine would have the largest. But as we go down a family, the atoms get bigger and bigger, so chlorine is going to be smaller than bromine. So selenium is bigger than bromine, which is bigger than chlorine. So chlorine is the smallest of the three. So it would have the largest ionization energy. Circle the element with the smallest ionization energy. So these are all alkali metals: sodium, potassium, rubidium. So remember that the atoms get larger as we go down. So which one has the largest radius? That would be the one that would have the smallest ionization energy, because it would be easier to remove an electron. So of the three, rubidium is the largest. Easier to remove an electron from rubidium than from potassium or sodium, because rubidium is so much bigger. Okay, the last trend, electronegativity. Electronegativity is a measure of the attraction for a shared pair of electrons in a covalent bond. So this is a little, you're going to have to bear with me as I go through this, because this is a topic that you won't fully understand until we get to our unit on covalent bonds. Now, let me just kind of give you a quick little overview here. An example, this is hydrogen fluoride, and the G here means it's a gas. Now, when it's written like this, it means that they are bonded together. In chemistry, we use a dash to represent that. So again, I'm just giving you a little bit of a peek ahead. You don't really need to know all this to know what the trend is for electronegativity, but I think you might appreciate knowing what electronegativity specifically is. So this bond here represents two electrons that are being shared. Remember the octet rule, atoms tend to lose, gain, or share electrons to have the configuration of a noble gas. So this would be an example of the sharing. But the sharing is unequal. And that's what electronegativity measures. How equal is the sharing of electrons? The element that has a stronger attraction for the shared electrons is said to be more electronegative. So fluorine is more electronegative than hydrogen, results in an unequal sharing of electrons, which you'll find is called a polar covalent bond. So we can kind of exaggerate this. So if this shaded area here represents the orbitals that are being shared. So the hydrogen has one half-filled s orbital, the p has one half-filled p orbital, and they overlap with one another, and that's what a covalent bond is. But that sharing is unequal. So the two electrons that are being shared between the two are more over on the fluorine side than the hydrogen side. So the two shared electrons are pulled closer to fluorine. So fluorine is therefore more electronegative. The trend. Again, it's inversely proportional to the atomic radius. The smaller the radius, the higher the electronegativity value, because the electrons that are being shared are closer to the nucleus. So increases as you move across a period, the atoms get smaller, electrons closer to the nucleus, and therefore more tightly held. So very similar to ionization energy. Decreases as you move down a family. Atoms get larger, electrons are further from the nucleus, more weakly held. Okay, before we do some practice, a couple of things about electronegativity. First off, we exclude the noble gases. Electronegativity trend excludes the noble gases. They have a completed valence shell and generally do not share electrons. Remember the octet rule, atoms tend to lose, gain, or share electrons to have the configuration of a noble gas. Well, electronegativity deals with the sharing of electrons, but noble gases don't do that. So when we talk about the electronegativity value increasing as we go across a period, we stop at the halogens. It does not include the noble gases. Now also, there are three elements that are particularly electronegative. The three most electronegative elements: nitrogen, oxygen, and fluorine. When we get to our unit on covalent bonding and what is called intermolecular forces, we'll find that it's very important to know these three. The most electronegative of all is fluorine. Fluorine is the most electronegative element and is assigned the value of 4.0 using what's called the Pauling scale, named in honor of Linus Pauling, who in 1932 first proposed the concept of electronegativity. He was just a wonderful, charming scientist. You would have loved him. Died a few years ago. Okay, let's do some practice. Circle the element that is the most electronegative. So again, we want to find the elements on the periodic table. So actually we used these three before when we talked about ionization energy: chlorine, selenium, bromine. A hint, which element has the smallest radius? Well, chlorine, remember, is the smallest. Atoms get smaller as you go across and smaller as you go up, or conversely get larger as we go down. So chlorine is going to be the smallest. However, for electronegativity value, kind of an easier way of doing it is ask yourself which element is closest to fluorine. So remember, fluorine is the most electronegative element, so that the atom that is closer to fluorine would be the more electronegative. And so that would be chlorine. Circle the element that is the least electronegative: lithium, sodium, magnesium. So lithium, sodium, magnesium, so these three. So the hint is which element has the largest radius. Remember that the atoms get larger as you go down, smaller as you go across. So that means that sodium is going to be the largest. So remember that the atomic radius is inversely proportional to electronegativity. So the larger the atom, the smaller the electronegativity. So sodium would be the least electronegative. Okay, so this is that slide I showed you earlier, so maybe this will make a little bit more sense to you, so please do copy this down. Atomic radius decreases as we go up and across. Ionization energy increases and electronegativity increases as we go up and across. Or it's kind of a simpler way of doing it is just, is going a diagonal as we go across, from the lower left to the upper right. And yes, for electronegativity, we would want to make note that it excludes noble gases. So as we're going across a period, yes, the electronegativity value increases, but we don't go into the noble gases. Okay, that is it. That is the end of notes.